How's it going, everyone? Y'all ready? It's going to be a small group today, I think, because Thanksgiving's tomorrow, but that might be a good thing. Let's see how it goes. So I was looking at our schedule. We only have today and 2 classes next week, and we're done. And I've finally come to I've conceded to the fact that we're just not going to get as far as I normally do in a Cal 2 class. I normally finish chapter 8. I just don't see any way of us getting through it. I mean, I could have you watch videos on your own time and stuff, but you know, we're just going to get into power series today. And then even though it says we only need 2 days for these sections, that's really not the case. I mean, we probably need 2 days for each of those sections. So we're just going to have to wing it here at the end and try and, it's not like I can give you the most important things because you have to know one thing before I can show you the next thing. So we're just going to go as far as we can. So with that said, let's get right into this. We're still in 8.4 right now, talking about convergence tests. There was one example I wanted to work through, which is an example of a series that you haven't seen this before. So I wanted to at least show it to you so that if you ever face it down the road, you'll have some idea of how to do this. So here we go. We've got this series, right? And we're asked whether or not it converges or diverges. Last class, we learned about the ratio test, which is really a great test. We're going to use the ratio test here, but what we need to do is get this into the form of a sum. We need to make this look like this. All right, and then we can run our ratio test. So we have to identify a pattern in here, and hopefully you can see that if you look at the numerators, you know, you start with 2, then it's 2 times 6, where 6 is 4 more than 2, right? And then you have 2 times 6, and then now if you add 4 to 6, you've got the 10, and the next one is 2, 6, 10, you add 4, you get 14. So it looks like each one of the numerators factors are jumping by 4 each time, right? And then in the denominator, we're jumping by 5. We're starting at 3 and we're jumping by 5. So we know how to make jumps. Okay, we learned that when we were in 8.1. So you might think that maybe you just do this. Watch, the top's jumping by 4, so I need 4n up here, but I need to start at 2, so I need to subtract 2. And that would start me at 2, wouldn't it? If I plug in 1, I'd be here at 2. And then if I plug in 2, I'd have 6. This should work, right? And then on the bottom, same thing, 5. We're jumping by 5, so 5n, but I want to start at 3, so got to subtract 2 there. But this doesn't work because if you plug in, if we just start plugging in, if we plug in 1, we're going to get the 2/3. Plus, now on the next one, we're going to get 6 over 8. But we're missing the 2 over 3, right? And on the next one, you're going to get 10 over 13. But you're missing the 2 times 6 and the 3 times 8. So we've never seen this sort of thing before. Never seen a series written out this way. So what we're going to do is write it in a way that is going to look weird at first, but let's just see if you understand this. So the numerator, what I'm going to think to myself is the numerator is always going to be 2 times 6 times 10 times, and I'm going to keep doing that until I get to 4n minus 2. All right, so let me just write that out, and then I'm going to write below it the bottom, which is going to be, I'm going to do 3 times 8 times 13 times, and I'm going to keep doing that, and I will stop when I get to 5n minus 2. So this here is telling you where to stop, right? That's telling you where to stop. And then these are just to establish the pattern of what you're doing, okay? This is to establish your pattern. So with this written this way, if we plug in 1, okay, if we plug in 1, then we're going to go 2 times 6 times 10. We're going to do that, and we're going to stop when we get here. But if we plug 1 in right here, we know that we get 2, right? So we're actually going to go 2 times, and then we're going to stop at 2. So we're just going to write the 2. And then the bottom, we're going to go 3 times 8, but we're going to stop when we get to this. But when we plug in 1, we're going to stop at 3. So we're only going to have the 3. Does that make sense? Then plus, now we let n be 2. So we're going to do this pattern again, but we're going to stop when we get to, let's see, 4 times 2 is 8. Take away 2, we're going to stop at 6. We're only going to have the 2 times the 6. And on the bottom, same thing, 3 times the 8. And then we keep going. That's weird, right? We haven't seen that before, okay? But that's the way you would do it, okay? So this right here is this right here in this orangish color. This is our A sub n. And now what we need to do is run the ratio test. So to run the ratio test, remember that with the ratio test, what we're looking for is, let's bring it up here. Okay, ratio test, we're going to be looking at a series. We're going to take a limit as n goes to infinity of the ratio of the absolute value of the ratio of the n plus 1 term over the n term. We're going to figure out what that answer is. If that answer is less than 1, we've got convergence. If the answer is greater than 1 or infinity, we have divergence. And if the L that we get is 1, then it's an inconclusive test. So remember that. If L is 1, it's inconclusive. That's going to be important later today. Okay, so let's run the ratio test. I need to take the limit as n goes to infinity of the absolute value. So what I need to do is rewrite this, but stop at n plus 1, right? Not at n. So watch the way I do this, because if you don't write it this way, you're going to get yourself into trouble with it. I'm going to go 2 times 6 times 10 times dot, 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 times. I'm going to leave a space here. And at the very end, the last one would be what I get when I plug n plus 1 in here. So 4 times n plus 1, take away 2. And then I'll fill in that parenthesis in a second. 3 times 8 times 13 times dot, 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 leave a space, and then whatever I get when I plug in n plus 1 into the last piece. Okay, that right there is a sub n plus, this right here is a sub n plus 1. Now I need to divide that, right? Now don't write this down. I need to divide this by just a sub n, right? But every time you run the ratio test, you're going to be dividing a fraction by another fraction. So I'm just going to get into the habit of not even doing the division. I'm going to do multiplication of the reciprocal instead, just to save myself a step. So I'm going to rewrite a sub n, but flipped over. So 3 times 8 times 13 times dot, dot, dot. This time, because we're stopping at n, I'm just going to put that. I'm not going to put another parenthesis in front of it. And again, you'll see why in a second. And then 2 times 6 times 10 times dot, 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 times the last piece, which will be 4n minus 2. Absolute value, let me clean this up, there we go. Okay, are there any questions why I did this way or flipped it, or are we all good with that? Okay, now do you see a bunch of stuff cancels? Do you see that like this 3 and that 3 are gone, this 8 and that 8 are gone, this 13 and that 13 are gone? Anything else that's in here should cancel out with anything else that's in here. Now, does anything cancel out this 5n minus 2? This is the important part. Does anything cancel out this? Well, what is, I want you to look at this piece right here. If I distribute the 5, I get 5n, let's see, plus 5 minus 2, I get 5n plus, what is that, 3, right? And if I do this one and distribute, I get 4n plus 4 minus 2, so 4n plus 2. So think about the pattern that we've established. Remember we said that the pattern was that with these 2, 6, 10, that they're jumping by 4 each time, right? So what would the one right in front of this one be? If this one's 4n plus 2, then what would the one right in front of it be? I see some of you talking, but everyone's muted.
4n plus 1.
the pattern is that, look, the pattern is that the number in front, like here's 10, right? The number in front of it is 4 less than it, right? Here's 6, the number in front of it is 4 less than it. So if this one's 4n plus 2, then the one in front of it should be what?
4n minus 2.
And minus 2, right? This one should be 4n minus 2. And then if this one's 5n plus 3, what's the pattern on the bottom? That it's 5 less as you go to the left. So if we take 5 away from this, 5n plus 3 take away 5, don't we get 5n minus 2 there? Right? And so that's why I put those parentheses there, because it's important to see that this 5n minus 2 is going to cancel with that 5n minus 2. And also on the numerators, the 2 here cancels with the 2, the 6 cancels with the 6, the 10 cancels with the 10. Everything in the dot, dot, dot cancels with everything in the dot, dot, dot here. And there it goes. The 4n minus 2 cancels with the 4n minus 2. So the only thing left after you do all this is the absolute value of 4n plus 2 over 5n plus 3. And that we can just do L'Hopital's rule, because we get infinity over infinity, right? You do L'Hopital one time, you're going to get 4/5. And that is less than 1, right? 4/5 is less than 1. So what we can say is that this series up here converges. Oops, sorry, I forgot to silence my phone. Okay. All right, any questions? So I wanted to show you this example again, because this is just a strange way of writing out a sum. I don't have time to show you this, but I'm going to show it to you anyway. If you wanted to do this 2 times, let's go this way. 2 plus 2 times 6 plus 2 times 6 times 10 plus 2 times 6 times 10 times 14, right? There is a mathematical notation for this, all right? What it is if you ever want to do something like this, a repeated multiplication, you know how we use a sigma for repeat, like addition? You're adding a bunch of things together. We actually have a symbol that we use if we want to do multiplication instead. And it's actually capital pi. So if you go capital pi, n equals 1 to infinity of, let's say, 4n minus 2, okay? Then what you do is you would start out with n being 1. If n is 1, what do you have? You just get 2, right? But instead of putting plus, you put times. Now you get, let n be 2, and then you plug in 2 and you get your 6, and then times. Now you plug in 3 and you get your 10. Does that make sense? It's just multiplication instead of addition. I just want to show that to you. We really, in the whole calculus sequence, you probably will never see that. Okay, but I just wanted you to know there is something that we do have it in math, a product, okay? A product instead of a summation. Okay, that's it for that. Now, still in 8.4, the last test that we have, okay, is the root test. And this test, I'm just going to show you one example. We don't use this test very often, but some problems are just like perfectly suited for the root test. And so when you see them, you want to break out this test. You don't want to try the ratio test because it'll get too complicated. So when you look at this, the thing that's going to tell you to use the root test, okay, the thing that tips you off is you've got some expression and the entire expression is raised to the nth power. That nth power is what's going to tell you root test. And the reason why is because the root test says, if you're trying to find out what this series does, what you can do is you can take the limit as n goes to infinity of the nth root of the absolute value of this thing in yellow, and then figure out what that is. And it's just like the ratio test. If you get an answer that's less than 1, you have convergence. If it's greater than 1 or infinity, you have divergence. And if it's 1, you're inconclusive. So let's just run this root test on this problem. So I'm going to just take the limit as n goes to infinity of the nth root. So that's what the test says. The test says I'm going to take the nth root of all of this, okay? And when I do the nth root of all this, and by the way, I'm supposed to do the absolute value, but I'm not doing the absolute value of this because I know that the absolute value, I know that this is a positive number, right? If I'm plugging in n's that are positive, this is always going to be positive. So I don't care about that. Now, the nth root and the n cancel. That's the whole beauty of the root test right there, is that part right there. Those things cancel. And so all you're left with is limit n goes to infinity of the 3n squared over 4n squared plus 1. And if you just do L'Hopital on that twice, you'll get, actually just once, you'll just get 3/4. And that's lesson 1. So this converges. Okay? Any questions? Okay, we have all the tests in place now. If somebody gives us a series, right? If someone gives us a series, we have all of these different things that we could potentially do to determine the convergence or divergence of the series. Now, why? Why have we done all this, right? Why have we gone through all of this? Just for fun, right? All right, so power series, we're moving on to 8.5. So here, I'm gonna try and motivate the idea first. So we already, hopefully we all understand that integration of functions is important. Unfortunately, we haven't had time in this class to get into like real applicable, like real world applications like computation of work or hydrostatic pressure, or, you know, there's a bunch of different things that we can do in engineering classes where we could apply the antiderivative to something. We did volumes, areas between curves, things like that, but we kind of stay away from like real world physical applications. We did the standard stuff we do in Cal 2. So I hope that you believe that being able to integrate a function is important. If you've bought into that, then I've also shown you that sometimes it's difficult, right? When we've done an integration, it's hard sometimes, and sometimes it's impossible. So a classic example of this would be if I just ask you for the antiderivative of this. And if I ask you for the antiderivative of that, or if we go to Wolfram alpha for that, there's not going to be an answer, all right? I mean, Wolfram alpha will give you something, but it won't make any sense. So there's no way to do this by hand. So there were two men who came up with calculus, right? There's Isaac Newton and a guy named Leibniz. They both developed calculus independently of one another at the same point in time, which is kind of weird. They didn't know that the other person existed and was working on this. And at the same time in history, two men came up with calculus. That's why we have different notations for it, because they each use their own notation, right? But there's a big difference between the two, all right? The big difference is that Newton, he developed power series and Leibniz did not. And so Leibniz would get to certain problems that he couldn't do, where Newton, after developing the power series, had a way of doing it. And so Newton usually is regarded as having a more powerful version of calculus, if you want to say it that way. But Leibniz had a better notation. A lot of people like the Leibniz notation. So whatever, it is what it is. But the question that Newton kind of came up with to kind of motivate this whole idea of power series was that, yeah, you know, sometimes it's hard to deal with functions. So is there a way, okay, so he was asking himself this question, can we find a polynomial function which would approximate some given function? So if we are handed a function that's difficult, can we somehow approximate it with a polynomial? And when we say approximate, I know that everyone kind of says, well, that's kind of cheating because it's not the same thing. But it turns out that this approximate turns into later, it turns into exactly, not just an approximation, it turns into to the function. Like it actually is the function. But, you know, that was the question. All right. Now, the reason why Newton asked this question was because if you could approximate a function with a polynomial, then it would be very easy to integrate that function, wouldn't it? So let me give you an example right now. of a function that you're all familiar with, cosine x, it turns out that this function is approximately, okay, it is approximately 1 minus x squared over 2 plus x to the 4th over, how do I want to do this? I'll do it 4 factorial minus x to the 6th over 6 factorial. Now remember, 4 factorial is just a number, right? And I could have put here 2 factorial, but 2 factorial is 2. And under this is 1 factorial, but 1 factorial is 1. So do y'all see this? This is a polynomial, isn't it? It's a polynomial. Do y'all see a pattern? Right? It's alternating. It's an alternating series, right? It's a finite series right now. It's alternating, positive, negative, positive, negative. Looks like the x's just have powers that are even, and then the denominator is always just even factorials. So you could probably predict what the next one could be, right? Next one would probably be what, x to the 8th over 8 factorial? And that is correct. That is actually right. And that would be a better approximation of cosine x. So if you just look at like the first one by itself, just that's just the number 1. And that's a shitty approximation of cosine x. All right, and I'll convince you of that with a picture. All right, let me just bring this up. Hold on. I thought I had this open, but it's not. So give it a second to load. Okay, here we go. All right. Where are you? Come on. All right. There you are. Okay. So what we're looking at here is cosine of x. We should all recognize that that's cosine, right? And right now, this black horizontal line that I have here is, do y'all see that 1 right there? That's the constant function 1. And that is a pretty bad approximation of cosine, right? You would say that these really aren't that good. The only thing they have in common, right? The only thing that these things have in common is that they hit at the same points. Hold on, I need to bring up one more thing here. I can't write on my screen until I open this program. Okay, there we go. Okay, let me try this again. So the only thing you could say is that they have those points in common, right? That's about the only thing that's good. So, but what I'm telling you here is that if you were to include a little bit more, so like maybe you decided not to worry about that, but you just included these two, that's 1 minus 1/2 x squared. That's what that is, right? That's a parabola, isn't it? That's a parabola. And let me go back to this. Let me go ahead and show you that particular parabola. Here it comes. Okay, so the dotted line, I'm just leaving behind the one we just had before. That was the crappy approximation. And now take a look at this parabola. Isn't that better? Isn't that a better approximation? Now, it sucks out towards the edges. Like, it doesn't follow it over here. But if you're just looking like in this region right here, it's pretty damn good, isn't it? Would you all agree? That's a way better approximation than the one we just had before. Okay, well, what happens if you say, all right, let's include the first 3 of these. Maybe that'll be even better. So here comes the first 3 of them. There it is right there. So I've left the other one behind. You see that the parabola we had started to like pull away from the red, but the next, this one right here, actually stays closer. Y'all see that? And the further out I go, right, if I just continue this pattern, the more of those I include, the better my approximation is going to be. So watch, I'm going to keep going. Watch what happens here. No matter how long I've been teaching this, that blows my frickin' mind away, okay? Because what we're saying is this polynomial function, 1 minus x squared plus x to the 4th over 24, blah, blah, blah. This is a degree 18 polynomial, right? That's a very high degree polynomial. However, look at how damn good it is at approximating cosine, right? It's awesome. And look, if I had to integrate this, I could integrate these. That would be no problem. I just use the power rule, right? Each one I do term by term. Now, of course, we could integrate cosine x, all right? We could, right? But this is just to show you fundamentally what's happening here and what Newton was trying to do. He's saying, if we have a complicated function, is there a way to rewrite it as a polynomial, right? That's pretty cool. Now sine, we have the same thing. Let me back this up because sometimes I can make my computer freak out. Sine, here's the sine function. Okay, so we can perhaps have a good approximation of sine. So look at my first approximation, 0. That's that flat, that's the x-axis. That sucks. Okay, how about x? That's the identity function. That's pretty good in here, isn't it? But not very good out here. Well, let me keep going. Okay, this is x minus x cubed over 6. Check that out. That black one's a little better. Let me keep going. Wow, right? I mean, look at this. Now this is a 19th degree polynomial, but look at how good it is, right? And if I go out further and further, it'll just keep conforming to that sine function, just kind of, well, not to steal the thunder from later, but actually if you kept going forever, okay, if you just keep following that pattern forever, that is what sine is, okay? And so Newton started by saying, can we approximate it with a finite polynomial? And then we find later that sine x is equal to an infinite polynomial. And that infinite polynomial is actually called the Maclaurin series. We'll get to that maybe. But every function has what's called a Maclaurin series, which is an infinite series that represents that function. It's amazing. All right. Now, have y'all noticed something about the powers here for sine? Has anyone noticed what the powers are there? And then when I was doing this, did anyone notice the powers here?
Sine has all the odd powers and cosine has all the even
powers. And cosine has even powers, right? Well, do you remember being taught in pre-cal that sine is an odd function? Okay, now you see why. It has nothing to do, like, why did they pick the name odd? It seems odd that they would pick the name odd and then even that they pick even. It's because they were talking about the power series for these functions. That's what determines whether or not a function is even or odd. When you look at its power series, do you have even powers, only even powers of x? So any function that when you write its power series has only even powers of x is an even function. Any series that you write that only has odd powers of x would be an odd function. Any function that you write that has a combination of odds and even is neither even nor odd. So let me see, do I have an example? E to the x, okay. This one's also pretty mind-blowing. There's e to the x, our classic exponential function. Does it have a power series? Okay, that's a crappy approximation. Here comes, okay, now 1 plus x. That's better. Let's go some more. How about 1 plus x? Oh, I went too far. There it was. Okay, 1 plus x squared over 2. That's a parabola. That parabola is a little better. Let's keep going. There's a 3rd degree polynomial, 4th degree. Let me zoom out. Yeah, let me zoom out because you can't really tell what's going on here. Can you all see the e to the x? Let me back this out. There's e to the x, and then watch these guys start to wrap themselves around this function. It's crazy. It's crazy, right? Now, look at this function here. It contains both evens and odds, right? Evens and odds. So, and you probably know that e to the x is neither even nor odd. If you look at it, it's not a reflection of itself over the x-axis or over the identity. So, wow. So that's what this is all about. How do we get from e to the x to this, right? How do we get from there to there? How do we get from cosine of x to this? How do we get from sine x to this? Here's tangent for you. There's the tangent function, right? There you go. There's tangent. We know that tangent's periodic. If we start cranking this out, here they come. See that? Okay, is this even or odd or neither? Looks odd, doesn't it? This is an odd, tangent is an odd function. So every function can be approximated as closely as you want to some power with some power series. Every function. All right, well, so we need to build up to this. We can't just jump right in and start creating these things. We have to understand general ideas behind power series. So I hope that gives you some insight into where we're going, what we're headed for. And, you know, on your final exam, I could very well give you a problem like this right here and ask you to give me the answer to this. And I might, because what you'll do on the test is you'll say, okay, well, first I need to convert this to its, I need to convert that in blue to its power series. Once I get it, or Maclaurin series, once you get that, then you're going to integrate each piece one by one, and then you'll give me that as your answer. So your answer will also be a series. And I'll tell you to only maybe go do the first 5 terms, because the series goes on forever. But I'll say just use the first 5 terms. And just as a final kind of like wow factor, I don't know, it's wow factor for me. I don't know if it's a wow factor for you. Wolfram alpha. Let's go try and integrate that again. Integrate e raised to the negative x squared. Okay, classic example. So it tells you, look, here's the answer. 1/2 square root of pi erf x. What's erf? It's an error function, so it's not giving you a closed form answer. It's kind of giving up on you. But if you scroll down, look at that. What is this? This is the antiderivative, but it written in its series form. Now, ignore this part at the end. It's saying that you can go further, okay? Like you can have this actually go out and give more. I don't know if it'll give you more. Usually it has show me more, but you have to understand that this right here continues, okay? Continues forever. So Wolfram alpha is smart enough to actually get the infinite series. And I'll say one more thing that's a little mind-blowing. And I think I mentioned this at the beginning of class or earlier in the semester, is that when we're looking at this cosine function and you go to your calculator and you type in, you know, cosine of 2, right? If you type that into your calculator, cosine of 2, it's going to spit out an answer, right? Your calculator has no idea what cosine of 2 is. What your calculator knows is the power series expansion. So it's just plugging 2 in here for x, 2 in here for x, 2 here, 2 here, 2 here, 2 here, 2 here. And there's this, in the program, it's written, you know, in the calculator, there's, it's written in there where to stop. Maybe it does like the first 5 terms, okay? And then if you want more precision, it'll go out further, but it can, your calculator can do multiplication, division, addition, subtraction, all that. That's all this is, right? It has no concept of what the cosine function is at all. It just understands its series. And that's for every trig function you have. Your calculator is working with this thing, not with any idea of tangent and circles or, you know, little waves. It has no clue, right? So this is very much tied into computer science, because if you are looking at functions in computer science, you're looking at series. You're not looking at these things as like the way we look at them, right? It's different. Okay, I need to get started. All right, so power series. What is a power series? Okay, we need to define it. So a power series is this. I'm sorry, I forgot to put here, power series centered at x equals a. Sometimes you'll hear me say this, or books will say this. Instead of saying a power series centered at a, they will say a power series about a, about x equals a. So you'll either see that or you'll see the word about. So a power series, I'm defining this for you, is a series that n equals 0. It starts at 0. It's the first time we've done this. 0 to infinity of c sub n. So you know how we've been using a sub n? We're going to start using c sub n. It's a dummy letter there. And we're using a for something else. So c sub n times, in parentheses, x minus a raised to the n. That's what a power series centered at a is. So if that's confusing to you, let's just start plugging in values for n. If we start at 0, and don't freak out that we're starting at 0. We always started at 1 because I told you let's start at 1. But if I say start at 0, we should be able to just adapt to that now. We're starting at 0, all right? So the first term would be c sub 0, x minus a to the 0, plus c sub 1, x minus a to the 1, plus c sub 2, x minus a to the second power, plus c sub 3 times x minus a to the third power, plus dot, dot, dot. Now, when you look at this, all these c's, all right, all these c's are just constants. They're just numbers. I shouldn't say constants. They're just numbers, all right? Now, they might be changing, like c sub 0 might be different than c sub 1. C sub 2 might be different than c sub 3, or they could all be the same number, but they're just numbers, okay? So I'm gonna put here c sub 1, or sorry, c sub 0, c sub 1, c sub 2, all of those are numbers. And by the way, while we're here, what is this x minus a to the 0? Isn't that just 1? Right? So this is really just like a number plus some number in front of x minus a to the first power, then some number in front of x minus a to the second power, so on and so forth. All right? So let me show you an example of a power series. Well, here's one, okay? Here's one right here. I'm gonna grab this, and I'm not gonna take so many terms. I'm gonna take just the first couple of these. So if we look at this as an example, geez, that's terrible. Okay, if we look at this as an example, what you'd have to see here is that we have 1, and then see, do you see how, well, let me write it out first. Minus 1/2 x squared plus 1 over 24 x to the 4th minus 1 over 120 x to the 6th. So do y'all see that we're missing like on a power series, we have x to different powers here, and all the powers are included, right? First power, third power, everything's here, but we're missing those here. So we would have to see this as being like 1 plus 0 x to the first power minus 1/2 of x to the second power plus 0 x to the third power plus plus 1 over 24 x to the 4th plus 0 x to the 5th minus 1 over 120 x to the 6th. Do y'all see that? We have to realize, since we're missing all the odd powers, we have to put zeros in front of them. So everything that we see here, those numbers right there, those numbers are c sub 0, c sub 1, c sub 2, c sub 3, c sub 4, c sub 5, c sub 6. Do y'all see that? And do y'all realize that these x's in here, this is really like x minus 0 to the first power And this right here is really like x minus 0 to the second power, then x minus 0 to the third power, x minus 0 to the fourth. So this would be a power series centered where? Where would this power series here is centered where?
At x equals 0.
At x equals 0. So this would be an example of a power series centered at x equals 0. So if you ever just see x by itself to the power, you know it's centered at 0. You have to see like x minus something or x plus something in parentheses for you to say it's centered somewhere else. Okay. Now I'm going to give you another example. The next example I'm going to give you of a power series is something that is kind of a classic example because it really helps us kind of get a feel for what's happening here. I'd like for you to look at this series. Sum n equals 0 to infinity of x to the n. Remember, I started at 0, didn't I? Not 1, right? Okay. So let's plug numbers in. If we plug in 0, we get x to the 0. Then plus x to the first power, plus x squared, plus x cubed. This is a pretty straightforward series, isn't it? Now, x to the 0 is just 1. So this is 1 plus x squared, plus x cubed, plus x to the fourth, plus dot, dot, dot. Okay, is this, where is this power series centered?
Zero.
At 0, right? Because all we see is x's to the powers, right? Just like we did here. So this power series would be centered at 0. Just look at these and just realize each of those could be written as x minus 0, right? X minus 0 squared, blah, blah, blah. I'm not going to keep going, but that's why it's centered at 0. Now, what about the constants? What about the c sub 0, c sub 1? This would be c sub 0, right? What would c sub 1 be? It's not the x, because that's the part, the x part is part of the, x being raised to a power. So what's c sub 1 for us?
Is it 1?
Yeah, it's the number in front of this, which is 1, right? What is c sub 2?
1.
1 again, right? All of these have 1s in them. So when you look at this one, the previous example are c sub 0, c sub 1, c sub 2, c sub 3. These were all changing, right? They were different values depending on where you were in the series. The example I'm giving you now, all the c's have the same value. It's just a different example, okay? Sometimes they're the same, sometimes they're not. So for this particular example, c sub 0 equals c sub 1, which equals c sub 2, which equals all of these equal 1, right? All of them are equal to 1 for this particular series. That looks a lot like something we've seen before. That looks a lot like something we've seen before. Ah, there it is. Do you remember when we were talking about geometric series? We said the form of a geometric series is, I feel like I talked about it before this, no? Hold on. Yeah, this was me proving it. Yeah, so this was it. So a geometric series looks like this. When I introduced it first, it was A plus AR plus AR squared plus AR cubed plus dot, dot, dot. That's what a geometric series is. And then we rewrote it this way, right, using a summation. Do you all see this? Do you all see that we have this? We have, okay, A is the same for all of them, right? And then we have R is being raised to the first power, second power, third power. That's exactly what we have. We have A, which is 1. So this looks a lot like A plus AR squared plus AR cubed. But for us, A is 1, right? And instead of using R, what are we using? X, right? If I replace all my A's here with 1s and replace all my R's with X's, that's this series, isn't it? Yeah. Now, look at the formula for it. Do you see the formula? Do you see, didn't we say that all geometric series had to look like this? Sum n equals 1 to infinity of a r to the n minus 1. We had to have minus 1 here. So when we plug 1 into this, if you plug 1 into this, you'll get a. And if you plug 2 into this, you'll get this one. And then 3, you get this one. But notice that if we change this n to n equals 0 and change that n minus 1 to n, you get the same series. You get the exact same series. This is what we call shifting the index. We shifted the index by 1. So we change the formula in here and it will still generate the same series. So right now, what I want you to do, just real quick while we're talking about this, I want you to go back to your formula sheet and right up here with geometric series, I want you to add this to your formula sheet. N equals 0 to infinity, a r to the n. These are equivalent. So if you ever have a sum and it starts at 1 and it's geometric, you need to make the exponent look like n minus 1. But if it starts at 0, then you're okay to leave it as n, all right? Both of these generate the exact same series. Okay, so this is a geometric series. Can we all agree with that now? This is the geometric series, just kind of written in a different way, a way that we, oops, that's not what I meant to do. Written in a way that we haven't seen before. Can somebody tell me when this series would converge? So I'm asking you, can you tell me anything about the convergence or divergence of this series? We know A is 1, right? What's R for us here? What's R in this series?
The X.
R is really X, right? So what makes a geometric series converge? What makes geometric series converge? When what's what?
Absolute value of x is less than 1.
That's right. So we know with the geometric series, when the absolute value of R is less than 1, it converges. But here, the R is the X, right? So do you all agree that this will converge if the absolute value of X is less than 1? So as long as you give me a value of X that's less than 1, then that thing will converge. For example, if I gave you X is a half, then what does that series become? Sum n equals 0 to infinity of 1/2 to the n, right? That's what that becomes. So if X is 1/2, then that series becomes this. This is geometric, right? With 1/2, the absolute value of that is less than 1, and that means we're going to get convergence. Now, we could figure out what it converges to, right? We could, but let's not do that. All I care about is that it converges. Do you all agree it converges? Yes? Okay, now let me give you another example. So we're still working within the same example, all right? What if X is -3/4? Then that series up there becomes sum n equals 0 to infinity. If I do -3/4 to the n, I know that this is geometric, right? The absolute value of 3/4 is less than 1, so we're going to get convergence, right? As long as I pick a value where the absolute value of it is less than 1, I have an answer, right? Now think about this. This is a big deal right now, okay? What we're saying is that this thing in red, right? This power series, if you plug some values of X into it, it will give you an output, right? So if you give it an input, as long as that input satisfies this, then you're going to get an output, right? Convergence means you're going to have an output, right? Input, output, right? Input, output. Input, output. There's other values of x that don't work. If x is 2. This is geometric. The absolute value 2 is not less than 1, right? It's greater than 1. And so what we get is divergence. And so what we have here is an input. And this means we have no output. Right? So if we really wanted to, couldn't we look at this in red as being a what do you I'm trying to get you to see get the word here. What are things that we've dealt with in our life where we have inputs and outputs?
Functions.
Functions, right? Functions. So couldn't you look at this as a function that has a domain? And the domain of this function would be all values of x where you take the absolute value and they're less than 1, right? So this is kind of mind-blowing now, because if we define a function to be this infinite series, this power series, x to the n, this is a well-defined function. Well-defined meaning it makes sense to plug numbers into this, right? If I plug in a half, I'm going to get a number, right? We said because it's going to converge. If I plug in -3/4, I'm going to get a number. It's going to converge. But if I plug in 2, it's going to be not defined, right? Because I have an output, it's divergent, right? So if I look at it graphically, if this is my x value and this is the function's value, then as long as I plug in numbers that are somewhere in here, not including 1 and not including -1, as long as I pick inputs from here, I should have outputs, shouldn't I? I should have outputs. And those outputs should give me something. Let's see, if we plug in, let's see what happens when I plug in a half, okay? We can actually calculate this, because remember the formula to get the sum of a geometric series, right? If you have a geometric series and it converges, then the sum is a over 1 minus r, right? That's the formula for it. So if we do this geometric series, a was 1, so it'd be 1 over 1 minus a half. That's 1 over 1/2, that's 2. So that means if I plug half into this function, it's going to spit out the number 2, right? And I can do that for all the numbers in between -1 and 1. And so what we wind up getting is a graph, right? We wind up getting a graph. So this is our first time that we're actually seeing that an infinite series can be looked at as a function, as long as it what? It makes this makes sense to be a function so long as this series converges, right? And the convergence will depend upon the x value we plug in. So sometimes we have convergence, sometimes we have divergence. It just depends on the input, right? So if I go back to this page again, one last kind of recap. This is a power series, right? This is a power series. It may or may not converge. This power series may or may not converge. It depends on what you do with x. If the x is, if we give you a certain x value, then this series here is what we've been studying, right? That's a series that we did in chapter 8, section 2 through 4. It was all about, can we determine if something converges or diverges? So what we're doing is we're actually looking now at these power series. We're going to have to inspect what happens, and we're going to have to look at the x's to figure out, you know, what each of these, like if I replace that x with a number, like what it turns into, and can I determine if it converges? Okay, I hope that that all makes sense. Are there any questions? I know this is a lot. So here we go. Given a power series, okay, given a power series, only one of these can happen. And this is for all power series that you ever study for the rest of your life, all right? Here's the first thing that can happen. It converges at x equals a only. So what I was trying to get you to see, I'll put this page back up in a second. What I was trying to get you to see here is that we had a power series, and that when we plugged in different values of x, we may or may not have had convergence, right? We may have convergence or divergence. This was just one specific example. What this is telling us is that for any power series, there's only three possibilities of what can happen. First thing that can happen is that this power series will only converge at a single point, x equals a. That's like 1 point, 1 point only. Here I showed you that this one converged for like this little interval, right? Anything in this little interval, it converged. This first part is saying, well, it can happen at only 1 point. Okay, and then we're gonna have two more things, but this is saying at 1 point. That means this would be like a power series where the only input that makes sense is a single value. It's a function that's only defined at 1 point, and it's x equals a. Now let's just convince ourselves that this would be true. If I replace x with a, what would I get? Zero here, right? And 0 raised to any power is 0. And 0 times anything is 0. And so this would just be 0 plus 0 plus 0 forever. And that's 0, isn't it? So every power series has to do this. Every power series has to at least converge here. All right? So that's either going to happen, or 2, it's going to converge on an interval containing a. So it'd be like this. Visually, it would be like this. A number line, here's a, and we would have some interval where it converges. Okay, some interval. Now that interval can be an open interval like that. Do y'all know that the parentheses mean we do not include the endpoints? Yes, okay. So we could have that happen. We could have this happen. Brackets mean we include the two endpoints. We could have a half open interval where maybe the left side is don't include and the right side is include. And the last possibility we could have would be, those are supposed to be straight. That's ridiculous. Okay, that and that. So recap, for any power series, it's either going to converge only at a single point, A, or it's going to be A with some stuff on each side, an interval, with endpoints included or not included, just depends on the problem. Or the last thing is that it converges. Anyone have a guess? Single point, or an interval, or
All real numbers.
everything, right? Converges on R, which means that it converges on negative infinity to infinity. That means it converges everywhere, which is, these are the best ones. Power series that do this are awesome because you have no restrictions on X. Like no matter what X you plug in, the series converges every time. Those are the best that you ever can look at. And if you go and you look at your formula sheets, we haven't gotten to this. We have these Maclaurin series. This is what I was showing you just a second ago. Cosine of X is equal to 1 minus X squared over 2 factorial plus X to the 4th over 4 factorial. I was showing you that this is true, right? Well, I was trying to convince you that you could approximate cosine with a polynomial. And I showed you what sine was doing in e to the X, right? Okay. I want you to look to the side here. You see this? R. This is telling you when these power series are valid, when they converge for what values of x. And you see how this says r is 1, r is infinity? We're going to technically write this out later. It's called the radius of convergence. It's how big the interval is. So when you look at those three cases, it was either a point, an interval, or everything, right? Does it make sense to you that infinity means the everything case? That's how much, okay, it's infinitely big. The interval is infinitely big. So our radius of convergence is infinity. And this one right here, hey, wait a minute. This was the one that we just looked at a second ago, isn't it? This one, 1 plus x squared, that one right there. Look what its radius of convergence is, 1. The reason the radius of convergence is 1, and you know, we haven't formally done this, but we've talked enough about it that I think it can make sense here. When we look at this right here, right? The interval, this interval is too wide, isn't it? That's how wide it is. The capital R is called the radius of convergence, which means it's like if you had a center point, how far in each direction can you go? That's kind of like your radius. And so you can go 1 in each direction. Make sense? If you go 1 in each direction, then you're safe to use that series. All right.
How would you write if it was just a point?
X equals 2, x equals 0, something like that. And on those formula sheets, none of the ones on the Maclaurin series table have a single point of convergence. Those are very, very uninteresting to us because it would be like giving you a function that only exists at one point. And that's it, right? It's not defined anywhere else. All right, so those are the 3 possibilities that can happen. Let me go back to step 2 here. Okay, I'm now going to just squeeze something in here. So this right here, this interval that I'm talking about, here's how you get the interval. What you need for this interval is you need x minus a, the distance, that's the distance between x and a, to be less than some capital R, where that capital R is called the radius of convergence. You'll see this when we work out a problem. So let me work through a problem and then you'll see how this all comes together, okay? Yeah, I'm ready. All right, so the first problem that we're going to do here. Let's do this one first. I like this one. Okay, here we go. Does this power series, you know what? No, hold on. That's not the way I want to phrase it. I apologize. Let me put it this way. For what values of x does this converge? Okay, here it is, your first official power series checking for convergence or divergence. Okay, 2n plus 1 x to the n over n factorial. Now, please realize that the big difference between what we're doing now and what we've been doing is that now we have this x expression here, right? That has not been there in any of the series that we were doing in 8.2 through 8.4. So there's no way I'm ever going to be able to tell you whether or not this thing converges or diverges unless I have some idea of how x is impacting this. So let's just run the ratio test, all right? I'm going to run the ratio test and just see what happens. So I'm going to do limit n goes to infinity of, okay, so I rewrite this, but I replace all the n's with n plus 1s, right? So let me do that. If I replace all the n's with n plus 1s, I'm going to get 2n plus 1 plus 1 x to the n plus 1 over n plus 1 factorial. And then I'm going to divide that by this, right? Which is the same as multiplying by the reciprocal. So I'm, again, saving myself some time. Cleaning things up now. Doing some algebra here. It's going to be 2n plus 3 in parentheses, x to the n times x over, so I split this x to the n plus 1 into x to the n plus x. That way I can get it to cancel. What should I do with the n plus 1 factorial? How can we rewrite it? Now remember this, this is a big deal here.
Would it just be n plus 1 because n plus 1 factorial and n factorial eventually cancel out?
They will cancel, yes. But remember this property, we had this from a while back, this right here. Make sure you know that because it's going to come up quite a bit. N plus 1 factorial is n plus 1 times n factorial. So I'm going to rewrite this bottom as n plus 1 times n factorial. And yes, Varun, that will cancel with that n factorial up here. Okay, let's start canceling. X to the n, x to the n, n factorial, n factorial. That's it, right? That's it. Nothing else goes away. All right, so this is equal to, all right, so at this point, here's what I'd like for you to do whenever you're working these problems. Once you get things to simplify algebraically, I suggest you put everything that has n in it out front, like this. And then times whatever you have left that has x in it, which is this. Now, what's going to happen when we take this limit? The bottom here is really, what is this really? This is really 2n squared plus, I think it's 3n plus 1. That's what would happen if I FOILed this out. So wouldn't, if I let n go to infinity, would I get infinity over infinity and then do L'Hopital? And if you did that on this, what would this thing eventually go to? Where is this headed? 2n plus 3 over 2n squared plus 3n plus 1. L'Hopital on that one time would give me 2 over 4n plus 3, right? That would be L'Hopital on that first time. And now let n go to infinity. That goes to 0, right? So that goes to 0 times x. Now, what is this gonna happen here? If you've got a number that's going to 0 times some value of x, what should this whole thing head towards?
0.
0. Now, x cannot go to infinity. X is a number, remember, x is a number we're going to plug in, right? We're trying to see like, what x's do I plug in? As long as x is not infinity, which it can't be because x is a real number, this, no matter what x you pick, because that other part's going to 0, this whole thing is headed to 0. Now, I left something out of this intentionally. What do we need for convergence? We ran the ratio test, so what do we need? We need this to be less than 1, right? We need that to be less than 1. We need this to be less than 1. We need this to be less than 1. We need this to be less than 1. Well, is it less than 1? It is, right? This is true. Always. And what I mean by always is regardless of our choice of x. No matter what x you pick, go ahead, throw an x at me. 10, great. Doesn't matter. If you replace that with 10, this is still going to 0. -4, fine. That times 0 is going to 0, right? Regardless of x, this thing converges, right? Regardless of x. So of the three options for convergence, which of the three do we have? 1, 2, or 3?
1.
3.
Regardless of x, right? Converges on R, no matter what x is. Give me any x, right? It converges. Here we have case 3 happening. That's what's happening in this. So the answer is, for what values of x does it converge? Well, you could do it different ways. You could say x is an element of R. That means x is any real number. Or you could say x is an element of the interval -infinity to infinity. Or you could even say x is less than infinity, greater than infinity, a negative infinity. Any of those would be okay. All real numbers, right? Throw any x in here, give me a number, it's converging. So I want you just to imagine this for a second. What if I replace this with a number? 5 to the n, right? What we're saying is that this would converge. Because if you went, this would be a problem from the previous sections. If I asked you to tell me if this converged or diverged, you would run the ratio test. You go through all this work, and at the end, this would be a 5, and this would be a 5, and 0 times 5, that would give you something less than 0, and it would converge, or less than 1, it would converge, right? And this will work for any value of x you ever plug in. So if we look at this as a function, right? If we were to look at this as a function, then we would actually have outputs for any x, which means if we graphed it, we would have a graph, right? We would have a graph. I'm really curious to know right now whether or not Desmos can graph that. I have my doubts. Let's try it. Desmos is pretty powerful. Sum, let's go 0 to, I'm going to have to stop it. I can't go to infinity in Desmos. Let's just go to m, and I'll control that later. And then what was it? It was 2n plus 1 over, or times x to the n, all of that, oops, and all of that divided by n factorial. Oh, it did it. Okay, let me do something else. M is going to go from 1 to, let's go 100, stepping by 1. Okay, so do y'all see right now that this is graphing? This is graphing some. I have to let m get bigger. So there it is. That we just said a second ago that this series, right? That series converges for all x, which means if we plug in x in here, we're going to get an output. And that's what Desmos is doing for us. We plug in x, like if you plug in 1, right? It actually converges to this output. And so the graph you see here is the graph of that function. That's the graph of that function. Now I have to keep going out further and further. Okay, Desmos is having some trouble. There we go. Yeah, it's having a little trouble. There's the graph of the function. There it is. Okay, that's pretty cool. I didn't think it was going to do that. I'm just out of curiosity. I don't think I can put infinity in here. Infinity. No. It did it. Okay. Does it know what to do now? Yeah, it doesn't know what to do. Yeah, it's not drawing me a picture anymore. Oh, it gave me an exclamation point. Yeah, okay. So it can't do it. It's okay. I'm still impressed. All right, let's do another one. So the example that I just gave you, right? The example that I just gave you, this power series converged everywhere, right? Everywhere. So I want to do another one. Where's my day 23? Where's my day 23? There it is. Yeah, this one's fun. All right, this might be the last one we can do. We'll see. So I'm going to write this down. Same question. For what values of x does this converge? All right. -5 to the n times x to the n over square root of n plus 1. And I'm going to do something next to this just so y'all see it. Okay, so all I've done here, and this is not important for what you're about to do with the ratio test. This is not important, but what I'm doing here is I'm peeling everything apart because I want everyone to see that this is a power series. This is c sub n, and this part right here is x minus a to the n. So this is a power series that's centered at 0, and this -5 to the n over the square root of n plus 1, that right there is our c sub n. See, as you plug in n's, this is going to spit out a different number each time. And then this right here is just going to keep increasing the powers on x. Does that make sense? Okay, let's take 3 minutes, 4 minutes, run the ratio test, see what you get. All right. I'll be running the ratio test here. You can look at it as you go. Y'all ready to talk about this? So I plugged n plus 1 into all of these, and I just did it since I've done it so many times, right? I know that that n plus 1 on this -5 is going to split it into 2. The n plus 1 on the x right here is going to split it into 2. N plus 1 is this. Then I multiply by the reciprocal of this, and then I cancel a bunch of stuff. Is that all right? Now, why did I put 5 and not -5?
Absolute value.
Yeah, the absolute value is going to kill the negative, so I don't care about that. And then I had this root here and this root, they both had n, so I moved those off to the left and I put the x that was here by itself. And then I had to figure out what happens as n goes to infinity. So I took these two roots and I just algebraically rewrote them. And then this arrow means I took the limit, right? When you take the limit of the inside here, you get infinity over infinity, you run L'Hopital, you just get 1. So is that okay? These roots will go to 1, and you had the 5 here, so we have the 5. Any questions up to this point? In order to have convergence, we need these to be less than 1, right? We need this to be less than 1. Now, we need to take a little side step here. You sure there's no questions? Oh, shit. No questions? Move this up here. Okay, little side note. When I tell you, or when someone says to you, the absolute value of x is less than 2, what they mean is this. The distance between x and 0 is 2. Normally, we don't write -0 in here, but this right here is there, right? X minus 0. So this means all x values that have a distance from 0 of 2. So on a number line, it looks like this. Here's 0. X can be 2 to the left or 2 to the right. So it can go 2 this way or 2 that way. So it's everything, not including -2, not including 2, everything in between. So another way I could write that is x has to be between 2 and -2, right? That's what that really means. So when I'm teaching in college algebra, right, which I haven't taught in many years, but when I teach this in college algebra, what I tell my students is when you see absolute value less than some number, I say just get rid of the absolute value, write it down, and then on the left side, put greater than the opposite of the number you see here, -2. And that's the inequality. Let me do another example. If you had absolute value of x minus 3 is less than 4, then what I would do first is I would just get rid of the absolute value, write down x minus 3 less than 4. And then on the left side of this, I would go greater than what?
-4.
Okay. And then here, to get x by itself, you just add 3 to everything. Add 3, add 3, add 3. And so what you get is -1 less than x less than 7. So the absolute value of x minus 3 being less than 4 means that x has to be between -1 and 7. Now, the reason I wanted to show you that is because I want to make sure we know what the next step is going to be here. We need the absolute value of 5x to be less than 1. So I'm going to get rid of the absolute value. I'm going to put greater than -1. And then I'm going to divide everything by 5. There we go. Y'all okay with that? This series will converge, right? It will converge as long as you pick an x that is bigger than -1/5 and less than +1/5. As long as you pick something in there, right, then you're good to go. So when we look back at our cases, which case do we have here?
2.
We have case 2, right? Now, do you see this thing that I had here? Absolute value of x minus a is less than r. Do you see that right there? R is what we call the radius of convergence, right? I'm going to get to that in just a second, but look at these. Didn't I say here that for 2, it's going to converge on an interval containing x equals a, but it could be this, 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 or this. It looks like our answer is this right now, isn't it? It looks like it is, but we're not done, okay? There's a next important step, very important step. This expression, this limit will be less than 1 so long as this is true. But what if this was equal to 1, equal to 1, equal to 1? What would happen if I told you that the absolute value of 5x was equal to 1? What would this test, what could you conclude from the ratio test? What does the ratio test say? If this thing turns out to be 1, what's the conclusion?
It's inconclusive.
It's inconclusive. So right now, we actually do not know what happens when this is true. We don't know. It's inconclusive, right? It's an inconclusive test. So what we need to do here is ask ourselves basically right here. I'm going to go back to this right here. I actually want to know what's happening at these endpoints. That's an endpoint. This is another endpoint. Look, we know that as long as you're inside, in between those two numbers, we've got convergence. We don't know what happens at those two numbers. We don't know. Because if I plug 1/5 in, I'm going to get that to be true, and that's an inconclusive test. If I plug in negative 1/5 into here, it's going to come out to be 1, and that's inconclusive, right? So now what we have to do is test each of these endpoints into the original series. So I need to take this series here. And I must now check the endpoints. Okay, so let's start with the first endpoint. X is negative 1/5. So just replace this with negative 1/5. Okay, let's see what happens. Sum n equals 0 to infinity. We have -5 to the n. We have negative 1/5 to the n. We have over square root of n plus 1. And guess what? We're back in the previous sections now, right? There's no more x's in here. So we're just going to clean this up. Okay, when I can put these two together, right? Because they're both to the nth power. So when I put -5 together with negative 1/5 and I multiply those, don't I get positive 1? Right? And positive 1 to the nth power is just what?
1.
1. So that's just 1 over this. So here's the question. Does that converge or diverge? How would you do it? What do you think it does? Don't tell me that this goes to 0. Please don't tell me that this goes to 0 and it converges. Right? I know that goes to 0. So how would you deal with this one? You have all the tests now, right? You have all those tests to work with. I'll tell you what I'm going to do, okay? I'm going to compare it to something. I'm going to compare it to sum 1 over the square root of n. And I'm going to compare it to that because that is p series, right? P being a half, which is less than 1. This is divergent, isn't it? Isn't that a divergent series? And I'm going to use, since I'm doing a comparison, I'm going to choose to do, let's see here. I'm going to try the limit comparison, this one right here. That's the one I'm going to try because I think it's going to work. If I didn't, I would have to use this one. I'd have to show that that inequality was true because I'm comparing it to something that's divergent, right? But I'm going to do the limit comparison instead. I don't know why, just my gut's telling me it's going to work. It's going to work. So I'm going to take the limit as n goes to infinity of this guy over this guy, which when I take that limit, that's really, I flip it, right? Do the reciprocal. So I get root n over square root of n plus 1, which is really the limit as n goes to infinity of the square root of n over n plus 1. And boom, L'Hopital on that one time, right? And I get 1. Square root of 1 is 1. So what did the test say? The limit comparison test said, if you do this limit and you get what? If you take this limit and you
Positive
get
real number.
a positive constant, did we get a positive constant? Yes, we did. So the conclusion is that whatever this one did, that one does. So what does this one do? It diverges, which means we better not plug in -1/5. If we plug in -1/5, this series will not, this power series will not converge. Okay. I'm not done. I now have to check the other endpoint. If x is positive 1/5, and we go into that series, things are a little different. Just a little different, but they are different. What's the difference?
You have a -1 on top?
Yeah, you can't get rid of that on top now. When you put the -5 times 1/5, you get a -1 to the nth power, right? To the nth. So now you have to figure out whether or not that converges. How would you do that one?
Alternating series.
Excellent. Alternating series test. So I would run the alternating series test on this, which means I have to identify the positive part of it, which is this right here, 1 over that. So 1 over the square root of n plus 1 is the positive part of that series. What are the two things you have to show? You have to show that it's decreasing, right? You have to show that 1 over square root of n plus 1 is decreasing. How could we do that? We have kind of two options here. We could show that we need to show that this is bigger than this. Y'all know what I'm doing there? It's taking the nth one of these and comparing it to the n plus 1. Is this true? I think that's true, right? Because this denominator is bigger than that one. I'm happy, that's decreasing. Okay, next thing I have to show is the limit as n goes to infinity of this piece. This thing is 0, and it is. Boom. So we've satisfied the two conditions of the alternating series test, which means that when we plug in x equals 1/5, we get convergence, right? We get convergence, which means we can include this. So the final summary of this is that this series converges on -1/5, 1/5 bracket. Or you could write x bigger than -1/5, less than or equal to 1/5. See, we know that when we plug in 1/5, it's okay. But when we plug in -1/5, it was not okay. So how's that for a problem, right? You're given a power series, you have to run the ratio test. The ratio test forces you to look at two endpoints. For each endpoint, you have to do a test from our previous sections. Talk about killing like 5 birds with 1 stone, right? This is a problem that you have to demonstrate that you understand all of this, right? So these are great problems to put on exams. Why did we not have endpoints on the last problem? Why didn't we have endpoints?
It was all real number.
Yeah, because when we ran this limit, right? This is the first problem we did. When we ran this limit, this went to 0. And because that went to 0, it didn't matter what x was, right? On the problem we just did, when we ran this limit, this did not go to 0, it went to a number, and then we had an inequality involving x that we had to look at. We had to look at that inequality, and that created endpoints. Okay, that created endpoints. Okay, I want to talk about, in the last couple of minutes here, I want to talk about this capital R, this radius of convergence. So remember when we were back here at that step? I'm going to write it down right here. We were at absolute value of 5x is less than 1. Okay, in order to find the radius of convergence, you must look at the inequality and get it to look like this. It has to be x minus a number in the absolute value, and then less than some number. And whatever number that is, that's your radius of convergence. So the way I look at this right now, this does not look like this. I need to get rid of the 5. So I'd have to write this as 5 times the absolute value of x less than 1. Because 5 is a positive number, so it doesn't matter. And then here I divide both sides by 5. And now this is in this form, because it's really like x minus 0 less than 1/5. So the radius of convergence is 1/5. We'll have more practice with that. Excuse me. All right. Let's do one more, okay? One more in 2 minutes, 3 minutes. Here we go. How about this? I'll make this one quick. Okay, for what values of x does this converge? That's the question, same question as before. I'm running ratio, I'm going quick, okay? I'm going quick because I don't have much time. I plug in n plus 1. When I plug in n plus 1, I know that that n factorial is going to become n plus 1 factorial, which I'm going to split up now because I'm trying to work fast. Oh, well, you know what? This isn't a fraction, so I can just now divide that by the original. Y'all see what I did there? Okay, cancel the n factorials, cancel the x to the n's, take the limit as n goes to infinity of, let's see what's left, n plus 1 and then times x. Questions at all? In order for us to have convergence, we need this to be less than 1, don't we? We need that to be less than 1. What's wrong with that though? Where's that headed?
N plus 1 is more than 1.
It's headed to infinity, right? It's headed to infinity. That thing's blowing up, okay? I can't control that really, right? Oh, well, wait a minute, I can control it. I can't control it if I pick x to be what? If x is what, then yes, this would be true. If x was what? If it was what?
Negative.
No? What number could I plug in here that would make this irrelevant?
0.
0. If x is 0, right? So I'm not saying x is approaching 0. I'm saying x is 0, right? If I choose x to be 0, then this inequality will be true. But if I pick any other value of x, this thing's going to blow up on me, isn't it? If I plug in here like 0.000001, it's still gonna blow up, right? But if the only thing that will work is if x is 0. So does this converge? It converges at x equals 0. And that's the only place it converges. And so that's that third case. Remember we had the 3 cases? The first example I gave you, it converged everywhere. The second example was an interval, which meant we had to check the endpoints. That sucked. And then this one converges at a single point. Those are the 3 possibilities that you can ever have. You can never have 2 separate intervals or anything like that. By the way, what do you think the radius of convergence is for this? Think about how wide the interval is.
Is it just 0?
It's 0. Our radius of convergence is 0. In the previous problem, our radius of convergence was 1/5. And I didn't talk about it, but in this problem where it was all real numbers, what do you think the radius of convergence is? How big is that interval?
Infinity.
infinity. Okay. So when you talk about radius of convergence, you're only ever going to have 0, infinity, or some number, right? Those are the only radius you can have. Infinity would be where it converges everywhere. 0 would be where it converges at a single point. And then the other case is just you'd have to work this inequality out. Okay, we are out of time. Thank you all for being here today. Make sure you've got all your homework through 8.4 done. You can try starting to do 8.5, but if you do 8.5, yeah, I mean, you have what I've shown you an example of every type, but the 3 cases, but in no way have I worked through enough examples, I think, to make you feel completely comfortable. But that's why I have homework solution videos out there also, right? So I highly recommend that over the break, you're done with 8.4 and at least start working some of the problems from 8.5. It's going to be the same thing, that it's the same question that I asked here, but they ask you in the homework for 2 things. They ask you for the interval of convergence and the radius of convergence. So the interval of convergence is going to be this answer right here, and the radius of convergence is this answer. They're 2 different things, right? This is just going to be either 0, infinity, or a number. This is an actual interval. See how it goes. Have a great Thanksgiving. I will see you next week for our last week of classes, right? Okay. Take care, everyone.
Happy Thanksgiving. Thank you.
Yep.
Professor,